Okay, welcome back. Want to continue from where we stopped. In today's class, we want to talk about oxidation of alkenes. Now, alkenes actually possess a double bond. The presence of a double bond in an alkene makes it makes alkene to be very, very reactive. So majorly alkenes undergo two types of reactions. We have the addition reactions and we have the oxidation reactions. All right. So in oxidation reactions, it's a case where the double bond is either splitted into two halves or one of the double bond is being splitted. Okay. So let's look at types of oxidation of alkenes. We have two types. The first one, oxidation with cleavage of just one bond. All right, now remember, a double bond is always having something like this. So in this first type of oxidation, we said it's oxidation with cleavage. Cleavage means breaking of bond. So it's a case where out of these two bonds, one of them will break, right? One of them will break, leaving behind the other one. So in this type of oxidation with cleavage of just one bond of the double bond, all right? So just one of these will break, leaving behind the other guy. Okay. Now the next one, oxidation the cleavage of both bonds of the double bond. Now, so in this case now, imagine if you have something like this. Now, this is basically a case where these two bonds split into two, and then it gives rise to this plus this. Right? So I'm going to be taking the first one, right? After which we look at the second guy. But do not forget that in exams, they will not really, start writing out this and ask you which type of oxidation is this guy. No, the reagent that each of them will be reacting with will help us to understand whether it's going to be A or it's going to be B, right? So let me quickly write out the reagents. Now, reagents for A. Now, what type of reagents will I see that is reacted with alkenes? And I will know very well that it's actually the first one. Now, the first reagent we have is called alkaline KMnO4. Now, this is the first reagent, right? Once you see called alkaline KMnO4, this KMnO4 is potassium tetraoxomanganate 7 or potassium permanganate, right? So that is actually the two common ways this can be said, right? Now, in exams, you can see something like this called KMnO4. Then they have this. Now, the next one, still under the A, now we have per acid. Per acid have this formula. Now, why do we call it per acid? Remember that, let's say, for example, now RCOOH is carboxylic acid. So if I increase the O from 2 to 3, if I say RCO3H, this now becomes per carboxylic acid. So if I have an example, CH3COOH, and this is called ethanoic acid, right? Now it simply means that if I increase this guy to 3 oxygen, this will be called the ethanoic acid. So you can actually see what I mean by per acid. So in case you see this, you don't mistake it with this. All right, so this is actually carboxylic acid, and this is carboxylic acid. I gave us an example. I said, if, for instance, this guy is ethanoic acid, it simply means that this that has 3 oxygen will now be para-ethanoic acid. Okay, so the next one, we have the third guy. We have, and this is osmium tetraoxide. Now, these are the 3 reagents that we're going to be using for the first one. So anytime you see any of these 3 reagents reacting with an alkene, that is a compound that has a double bond, right? What is basically going to happen there is that one of these bonds will break. So I'll say note, the product of this reagent with alkenes is always a diol. Now, so if you use any of these 3, 1, 2, 3, and then you react it with an alkene, the product of that reaction is always going to be a diol. A diol is simply a compound that has 2 OH group. Okay, so that is that for that. So any of these 3 reacting with an alkene will break this bond. So what is going to happen here is that if I have any of this, let's say I have this KMNO4, for example, called alkaline. Now this is called alkaline. So what is simply going to happen is that this bond will break, this one of them will break, and then we have something like this. I'm just giving us an example. Now 3 of them will always give diol, but the only difference amongst 3 of them is that some will actually give OH on the same side like this, while some other one will give OH on opposite side. We're going to look at that in details. But just know that any of these 3 will give us a diol. Okay. Now let's look at the reagent that will break this bond, these 2 bonds at once. Reagent for B. We have, remember, this was called alkaline KMNO4. So this will now be, the second guy is hot acidic KMNO4. So it's just like if you have a cold water, if you pour somebody cold water and somebody hot water, the effect of hot water will be much greater than the one of cold water. So if cold alkaline breaks one of the double bond, hot acidic KMNO4 will split or break the 2 bonds, the 2 double bonds, the 2 bonds of the double bond. So basically, the hot here is telling us the intensity of this guy to show us how strong it is. So once it comes in contact with a double bond, it splits it into 2. Now the next one is ozonolysis. Now ozonolysis is basically breaking of a bond using ozone, right? Breaking of ozone, we know ozone to be O3. Breaking of a bond using ozone. So lysis means breaking. Ozone, breaking of bond using ozone, ozonolysis. Now this ozonolysis is majorly of 2 types. So this is what you're going to be seeing. Ozonolysis followed. Now the first one is ozonolysis followed with peroxide treatment. Now this is peroxide, hydrogen peroxide to be precise, H2O2. So when you actually break, after breaking the bond, you're going to treat it with OH2O2. That is peroxide. Now, but in exams, how is it always written? They can actually give this question in 2 ways. It's either they use an equation format or they use word format. In words, they'll write it out. In equation, they'll write it out directly. So whichever of them they make use of, if it's in equation, they will use this. If it is in word format, they say ozonolysis followed by this. And the next one is ozonolysis followed by treatment with zinc in an acid. Ozonolysis followed by treatment with zinc in an acid. So how do you write that guy? This is how they normally write it. So that is it. Now note that the acid can be represented using H plus, or they can equally use a known acid. So basically we have three reagents that can split the double bond into two. The first one is hot acidic KMnO4. The second guy is ozonolysis followed by treatment with peroxide. The third guy is ozonolysis followed by treatment with zinc in an acid medium. Right? So since we've actually seen the summary of what this reaction is all about, we're going to be taking them one after the other so that we can break it down to your understanding. All right, so let's start off with the first one. All right, now remember we said for us to actually achieve this, there are three reagents we need to look out for. The first one is A. Let's say the first one is cold alkaline. This alkaline most times can be represented using OH, KMnO4. Now KMnO4 can be named as potassium permanganate or potassium tetraoxomanganate 7. So these are the two common ways. The most common one is potassium permanganate. The IUPAC name is potassium tetraoxomanganate 7. All right. Now this reagent gives cis diol. Now, like I already told us, when you react this with an alkene, it's going to break just one of the bond and it's going to introduce two OH. Okay, because a diol is a compound that has two OH group. Okay, so once it introduces the two OH, they will be on the same side. When two same OH is on the same side, that is cis. When they're on opposite side, that is trans. Right? So I'll give you as an example. I'll say CH2. Now this is 18. I will come here. I'll say KMnO4 cold alkaline. This is cold alkaline. Now when you break one of these bonds, okay, and this becomes CH2 OH. Now the work this guy did is just to introduce OH on both carbons of the double bonds. Break this bond, add OH here, and that is it. So this becomes ethane 1,2 diol. Do not forget that diol can also be called glycol, right? So this compound is ethane 1,2 diol or ethylene glycol. Right, so diol can also be called glycol. So the work of this OH, KMnO4 cold alkaline, is just to break this bond, add it on both sides, the same side. Now, the reason why we say this guy is cis is because the two OH on opposite side. Right? Now, I'll give us another example. Let's say I have CH3, CH, CH2. And then this becomes KMnO4 cold alkaline. Once again, one of these bonds will break, OH add here. I'm only interested in the two carbons of the double bonds. All right, I have no business with other carbons. I'm only interested in these two carbons. So once I break this bond, add OH here and add OH here. This becomes CH3 CH CH2. So you have OH, you have OH. So once again, 3-carbon alkane is propane. You name it completely. You add the E, that is propane. All right. So if you number this carbon from the side that give this OH the smallest number, this is position 1, 2, and 3. So this is more like saying position 1, 2, and 3. So the two position of the OH is 1, 2, diol. So this is basically how we get oxidation of alkanes using KMnO4. Remember, this KMnO4, it's an oxidizing agent. So all the reagents we used, I wrote down earlier, they are all oxidizing agent, because anything that can actually act on a compound and actually allows the other compound to oxidize is an oxidizing agent. Now note this. Now this particular reaction is used for a test for an alkene. Right? This reaction we just complete now can also be used as a test for unsaturation. Do not forget, an unsaturated compounds are compounds that contains either a double bond or a triple bond. Right? So if I really want to know if a compound contains a double bond or a triple bond, I'm going to subject that compound to test for unsaturation. Right? Because one unsaturated compounds, like I said, compounds that have a double bond and a triple bond. So one of the tests that we can use to identify if a compound is an alkene unsaturated, because alkene has a double bond, the test is known as Bayer test. Bayer tests for unsaturation. So what does this Bayer test does? Now is this reaction. Class, cold alkaline KMnO4 is purple. Is purple in color. Right? Remember, anytime we're talking about tests, chemical tests, the ones we conduct in chemistry lab, we make use of our eyes to observe, our nose to perceive, and of course, our palm to feel in case there is heat change, right? Exchange of heat. So this particular cold alkaline KMnO4 is purple in color. Now, once it reacts with an alkene, right? Once it succeeds in converting an alkene to a diol, the color is going to change. The color of this will no longer be purple. So once cold alkaline KMnO4, which is purple in color, reacts with an alkene, the purple color changes to brown precipitate, which is MnO2. So the appearance of a brown precipitate or a brown color solution once you react alkaline KMnO4 with an alkene indicates the presence of a double bond. Let me break this thing down. I said cold alkaline KMnO4 can be used to carry out tests for an alkene. Why? Because this particular reagent is purple in color. Right? Now, once you react this particular reagent, cold alkaline KMnO4, with an alkene, the color of the solution or the color of that KMnO4 will no longer be purple, but it will change from purple to brown. Now, the change in color indicates that the compound that reacted with that KMnO4 is an alkene. And alkenes possess a double bond, and any compound that possesses a double bond can be said to be unsaturated. So because of this singular change in color, we said that this reaction can be used as a test for unsaturation. That is, it can be used to test for compounds that contains a double bond or a triple bond, but most especially a double bond. So in case somebody asks you, Bayer test is a test for unsaturation, true or false? The answer is true, because Bayer test can be used to test for unsaturated compounds, alkene most especially, right? The color of KMnO4 is purple. After it reacts with an alkene, the color changes from purple to brown, right? So the change in color indicates that the alkene is present, right? So that is that for the reaction with cold KMnO4. So let's look at the next reaction, which is Now I said the second reaction is reaction with osmium tetraoxide. All right. Now I said this reaction is a two-step reaction. Okay. It's going to actually occur via two steps, which I'm going to be showing us shortly. The product of the reaction, the product of the oxidation of alkenes using this particular reagent is a cis-diol. Now cis-diol, just like the one we got when we used cold alkaline KMNO4. All right. Now cis-diol is basically a compound that has two OH on the same side. All right. So I'll give us a reaction. I'll say CH2. Now the first one is reacting this. The second one using sodium silicate in the presence of a base. All right, so it's this is the combination. So you use is osmium tetraoxide followed by treatment with this. So if you don't follow it up with this, you cannot get the right product. Take note of that. So this is actually an oxidizing agent. So once it reacts with an alkene, once again it's going to break just one of the bond. It's not going to break, it's just going to break one, just like KMNO4 cold alkaline did previously. So this is what we're going to have. CH. So that is it. Once again, a cis-diol. So if I have another example, let's say now if we have something like this, right, just like I did previously, one of these bonds will break, and of course once this bond breaks, OH comes here, will form a cis. So this becomes CH3 CH CH2. So you can see what we've got here, the same products just like we did previously, but then different reagents. So cold alkaline KMNO4 and osmium tetraoxide will give us end product of cis-diol. Now per acid is now the one that will give us a trans-diol. Okay, it's something that has formulas like this, RCOOOH, like 3 oxygen at the center. All right, so now once you actually proceed, now before I proceed, let me say this. Now oxidation of an alkene using per acid first is going to give us an epoxide, right? So the first thing is that it's going to give us an epoxide. I'm going to show us here. Now when you now treat it with water, or when you now react it with water or aqueous solution, the epoxide opens up and gives us a trans-diol. So this is what I mean. So if I have CH2 plus CH2, now giving us per acid. Now this R is an alkyl group, which I can change to anything of any alkyl group of my choice. I'm going to do that in the second example. Now, so I said this reaction will first of all give us an epoxide. So this is how epoxide looks like. CH2, CH2. Now this is how epoxide looks like. One of these oxygen, right? You break one of the bond, infusing one oxygen, and then the bonds clamp the oxygen. Now when you react this with water or aqueous solution, this is what we are going to get. CH2 CH2. Now this becomes a trans-diol. So once you do this, you're not going to have a trans-diol. The OH will now be placed on opposite side, right? If you notice the difference between these reactions and the one we have is that the OH is on the same side. Cis. If you could remember cis and trans alkanes. Now since the OH is on the same side, we call it cis. But in this case now, since the OH is on opposite side, we call it trans. So that is majorly the difference between the two previous reagents and this last guy. Remember, the first product with per acid is going to give us epoxide. So this is epoxide. And this is a trans-diol. So let's look at this. we have something like this. So let's say we have CH3. All right, now this is actually ethanoic acid. I've decided to replace this R with CH3. All right, so what we're simply going to do here is that if we remove one of these bonds, we have CH3, CH, okay. Now when you treat this, so this is if I want to name this guy, this is butane. Just name the alkane. 4-carbon alkane is butane. Now this 2 carbon that is holding this oxygen, right? This is carbon 2 and this is carbon 3. So this becomes 2, 3 epoxide. Now in this case, this will be ethane 1, 2 epoxide, because this is ethane and the 2 carbons that are holding this oxygen is carbon 1 and carbon 2. Now once again, this can open up in the presence of water. All right, so let's do this. The present, if you add water to this, this can open up. So we now have CH3, CH, CH, CH3. Now this is this and this is this. And once again, the name of this becomes butane 2,3 diol. So that is actually what we have there. Right? If you have any question, you can drop it on the comments. So now we want to look at a case, oxidation of splitting the bonds, the 2 bonds of the double bond. All right, so let's see how the product is going to look like if you split the 2 bonds all at once. Now, what are the reagents that we make use of here? With the first one, we have hot, acidic, cheminophore. And the second one is ozonolysis followed with treatment with peroxide. Now the next one is now remember I said this H plus can actually denote an acid, just in case you're being asked or you're being told. This is an acid. They can replace it with a real acid. So this is ozonolysis followed by treatment of zinc. So these are the 3 reagents. The first one, if you use any of these 3 reagents, now the double bond is going to be splitted into 2, right? So the products of alkenes, when these reagents are used, can either be aldehydes, ketone, or now, just like I said, if you make use of any of these 3 reagents, hot, acidic, cheminophore, ozonolysis followed by treatment with peroxide, and then ozonolysis followed by treatment with zinc in an acid medium. All right, now you're going to split the double bond into 2 halves. right? And the product of the reaction can either be aldehydes, ketones, or carboxylic acid. So I'm going to be putting us through to see how we're going to achieve this. So sit back and watch us unfold this, all right? The concept behind this particular type of oxidation is that after this reagent must have splitted the double bond into two, right? They will convert each half to their respective either aldehydes or ketone or carboxylic acid. But here is a catch. Now the products that these compounds will be converted into, the product that each halves will be converted into is solely dependent on the number of hydrogens that are present on the carbon of the double bond, right? If the carbon of the double bond is having one hydrogen, the product is not going to be the same as if it is having no hydrogen after splitting it into two halves. Now this is what I mean. If I have CH3, CH, if I have something like this. Now, remember, class, the two carbons of the double bond is what we are interested in. I'm not interested in other part of the molecule, right? Those part of the molecule is none of my interest. I'm interested in the functional group because we are talking about reactions. Functional group is actually where reaction takes place. As a matter of fact, the definition of functional group will actually help us understand what I mean better. A functional group can be defined as an atom or group of an atom, or a part of a molecule that determines the chemical reactivity of that molecule or compound. So for alkene to be an alkene, to react like an alkene, is because of the presence of this double bond. So for alkene to be able to undergo oxidation, is still because of this double bond. So the oxidation process takes place in the double bond. So when I use this reagent, I'll split this double bond into two. Every other thing that was on this compound remains, and every other thing remains. So now look at this. After splitting this guy into two parts, what is now going to be the fate of each of the halves? Are we going to leave it like that? No. Now, for example, if I split this guy into this, CH3, CH plus C, CH3, CH3. Now, this doesn't make sense. You can't leave it like this because it makes no sense. Yes, it doesn't make any sense. You yourself, you know that this does not make any sense. So you cannot leave it like this. Do you understand? So what we are simply going to do is that after splitting this guy into two halves, this same reagent is going to convert this to a known compound, either aldehyde, ketone, or carboxylic acid, and then convert this guy into a known compound. So those three reagents will actually behave the same way. Like I said, it's not enough for us to split this bond and then have two sides. This is not complete. Carbon cannot just have two bonds, because if you put the bond complete, this is what we are going to have. Carbon here is supposed to have 4 bonds. So far you can see 2 bonds here. So this guy is not complete. So after splitting this into two halves, what now becomes the fate of each of the halves? So that is basically what I'm about to show us now. Class, pay attention. The product that each of these halves will be converted to will be aldehydes, either aldehydes, ketone, or carboxylic acid, depending on whether or not this carbon, original carbon of the double bond, is having one hydrogen or no hydrogen. So I'm going to show us the effects of this reagent in an alkanes, and if one hydrogen is present, what will be the product? If no hydrogen is present, what will be the product? All right, so let's look at it shortly. All right, so let's look at this briefly. I remember I said when you react either of hot KMnO4, ozonolysis with peroxide, or ozonolysis followed by treatment with zinc in an acid, You're either going to get aldehydes, ketones, or carboxylic acid. But this product depends on the number of hydrogens the carbon of the double bond initially would be having, right? If the carbon of the double bond has one hydrogen, the product we're going to get is actually going to differ a bit. If it has no hydrogen, all of them will give the same product. Okay, now look at what we have here. We said I actually put it in a tabular form to actually aid understanding. Now, number of hydrogens on each carbon of the double bond. I gave us an example. Right now, look at this guy. The two carbons of the double bonds are the ones with asterisks, but we consider them individually. So after breaking it, you look at the left-hand side. The carbon, is it having one hydrogen? If it is having one hydrogen, you do the same thing. You actually carry out any of this. You look at the right-hand side. If it's having the same hydrogen, same number of hydrogens, you're going to do the same thing. If you look at this guy, the two carbons of the double bonds, they are both having single hydrogens. So I said, if I was using hot acidic KMnO4, after splitting, this is going to convert the carbon of the double bond with one hydrogen to COOH, right? But in this case now, this compound is having two carbons with one hydrogen. So it means that after breaking this into two, it will convert the left-hand side, this CH, to COOH. It will also convert this other CH to COOH. Now, bear in mind that every other thing that is attached to this will still be attached. This CH3 will still remain, and this CH3 is still going to remain, right? So after splitting this into two, this CH is converted to COOH, carboxylic acid, and this CH is also converted to COOH, carboxylic acid. Now, when you're using ozonolysis followed by peroxide, now it is important for me to say this, that these two reagents, they give the same product at all times, whether it is having one hydrogen, whether it is having no hydrogen, right? I wouldn't want to talk about when it has two hydrogen because that is a bit above the scope of this class, right? So we're only going to focus on when the alkenes are having just a single hydrogens or no hydrogens at all. So when I'm using ozonolysis followed by peroxide, the same product I got for acidic KMnO4, that is the same product I'm going to get when I'm using this guy. Now let's look at the last guy. Now this is the one that is a bit different from the first two. Now in this case, we said after splitting, each of them splits it into two halves. If the carbon is having one hydrogen, that's the carbon of the double bond, original carbon of the double bond, was having one hydrogen. After splitting it, these two converted it to COOH. But this guy will not convert it to COOH. Instead, it will convert it to CHO. COOH is a carboxylic acid. CHO is an aldehyde. Right? Now, this zinc is a reducing agent. So zinc will not allow the process to complete to COOH. So zinc is going to stop it at an aldehyde stage. So take note that when anywhere you see zinc, zinc will not allow it to get to carboxylic acid. Zinc will stop it at the aldehyde stage. That is only when the carbon has one hydrogen. If the carbon has no hydrogen, like as you can see here, this has no hydrogen. After splitting it into two, this guy will give ketone, this guy will also give ketone, and that guy will give ketone. All right, so the way I'm saying it, ketone, makes it sound a bit crazier. Now, what I simply mean is that after splitting this guy into two, this reagent will simply add oxygen to each of the carbons. In this case, this added two oxygens. This also added two oxygen. This guy added one oxygen, but this one oxygen is at the outer, not inside. Now this is aldehyde and this is ketone. If the oxygen is added after hydrogen, like in this case, this is aldehyde. Now if the oxygen is added in between two carbons, this R is a carbon, right? R is an alkyl group. So if O is added between two carbons, it's a ketone. We also have COOH. Now when two oxygens are added between C and H, that is carboxylic acid. So for us to understand this better, all right, I'll be taking an example so that we understand this much better. So let's take this example. I'll say CH3. Okay, let's manage this small space. CH3 CH. Now when I react this guy with, remember these two carbons, they're having one hydrogen each, so I put asterisks here. So the effect, this is ozonolysis followed by peroxide, so this is going to split this into two. Now once that happens, we have CH3 CH plus CH CH3. But we cannot leave this like this because this doesn't really make sense. Now after doing this, class, remember this stuff we have here is actually inverted. So if I want to write this properly, I can still write this guy as CH3 CH. It's still the same thing. So I'm going to turn it properly. So instead of starting with CH CH, I will now say CH3 CH. Right? Okay. So now this is still the carbon of the double bond. Don't forget that. This is still the carbon of the double bond. Now let's look at what the rule says. After splitting, convert the carbon of the double bond with one hydrogen to COOH. So I'll come here. This O3 peroxide is the same thing, the same instruction that we're going to follow here. So we say this carbon that has asterisk was originally the carbon of the double bond, right? And this guy is having one hydrogen. And the rule says if it has one hydrogen, convert it to COOH. So this is what we're going to have. This becomes CH3 COOH plus, this is for the first side. We also have the right hand side, because when you split this into two, you have two sides. There's hydrogen here, so this becomes CH3 COOH. So this becomes the product of that reaction. Split it into two, we have this, we have this. Like I said, it's best you write it in an inverted form so that this CH will be on the right hand side. So I had to write this CH3 first, then CH. I can decide to cancel this one out. Now this carbon is now having one hydrogen, and the rule says if it has one hydrogen, convert it to COOH. So I convert this guy to COOH and also convert this guy to COOH, and that becomes a product of that reaction. So here, so the product of this reaction now becomes CH3COH plus CH3COOH. Now this is ethanoic acid, that's carboxylic acid. Now carboxylic acid is a general name for the compound that has COOH, but a specific name for the one that have two carbons is ethanoic acid. So now remember, this same product we are having here would have been the same if we had used hot acidic KMnO4, because hot acidic KMnO4 and this gives us the same answer. Do you understand? So I'll say if I come here and remove this and put hot acidic KMnO4, this will still be the product. Yes, this will still be the product, because hot acidic KMnO4 and ozonolysis followed with peroxide gives us the same product. Now let's look at what would have been the answer if we had used ozonolysis followed with zinc, because amongst all of this is the only difference when there is one hydrogen and when I'm using this. When there is no hydrogen, all of them, three of them will give the same product, right? So let's quickly look at this. So let's say ozonolysis followed by zinc in an acid. So the first thing first is for us to split the compound into two halves. This becomes CH3 CH plus CH CH3. Now you split this, the left hand side is this, the right hand side is this. But we cannot leave this right hand side like this because it's in inverted form. So we have to invert it or write it properly so that the CH3 will come first and this guy comes here. It's still the same thing, but we just want this to come to the right hand side so that, right, the incomplete part should be on the right, the complete part should be on the left. This carbon is already complete by having 4 bonds, but this one is not complete. So if I write this guy, this becomes CH3 CH. I strike this. Now the rule says after splitting, convert the carbon of the double bond with one hydrogen to an aldehyde, that is CHO, right? Now you look at this reagent. This is ozonolysis followed by treatment with zinc in an acid. So the first thing first, this ozonolysis is going to split this guy into two, which you have done. And after splitting it, the carbon of the double bond, original carbon of the double bond, will be converted to an aldehyde according to this. So this guy now becomes CH3 CHO. We have CH3 CHO. Do not forget that this can still be written as CH3 they still mean one and the same thing. So this is an aldehyde functional group and this is an aldehyde functional group. So you can see the difference between this particular reagent and these two reagents. The only difference between this and this is when the carbon of the double bond is having one hydrogen. When the carbon of the double bond is not having any hydrogen, like in the second case, all of them will give us the same product. Okay, so that is how we got this. So if I want to write the product, this will be the product of the reaction. Is that I'll write it in this form, this plus this, or this plus this. Whichever of these two you choose to write, you're very correct. Okay, so I'll stick to CH3 plus CH3 all right, so that is that for the first batch. So let's quickly look at for the second batch when there is no hydrogen. Then I will now wipe off the board and give us plain example. Now let's look at, now we have CH3 now remember, if I choose any one of these, this carbon is not having any hydrogen. So any of these three reagents that I choose to use will give me the same product. So I'm not going to write this reaction 3 times. I'm just going to explain it once. And of course, once I'm done explaining, you should know that if I choose to use these reagents or this reagent or this reagent, they are all going to give me the same product, provided that the carbon of the double bond, they are not having any hydrogen. So if you look at this guy, they are not having any hydrogen. This hydrogen is on this carbon, not on the carbon of the double bond. All right, so I'll go with hot, acidic, cheminophore. So first thing first, I'll split this guy. So once you split this guy, this becomes CH3 plus C. But once again, remember what I told us, that always invert what is on the right to the left. If there's anything here, take it to this so that you can get the right structure. So if I invert this, this becomes CH3, C, CH3. All right. So this is it. So I can now clean it. We have C, H3, C. You can choose to put it up or down. It does not matter as long as it's on the carbon. Now the rule says, after splitting, convert each carbon to ketone. Converting it to ketone is simply by adding oxygen here. All right. So ketone is COR, where this R is another carbon. So this is what it means. So this is CH3. Now this is a carbon of the original carbon of the double bond, right? Now you put O in the middle. You can choose to still put your CH3 like this, your C correct, or you can choose to put your CH3 here. Now this stuff you're seeing here can also be this is how it is written. The O that is added is doubly bonded to this carbon. So you can either put, after splitting it into two, you can either put your product like this. Now this CH3, you can still put it down, it's still correct. You can still put it by the side. But bear this at the back of your mind that this CH3 is not attached to the oxygen. It is attached to the carbon. Because if you write this out properly, the oxygen is doubly bonded to this carbon, which is pointing up, and the CH3 is on this carbon. So same thing is applicable here. We have CH3, C, you add your O here, then have your CH3 here. Okay, now once you've done that, just like I said previously, you can actually project it so that the O will be on the top. So having done that, what is the product of this reaction? The product of this reaction would be CH3, O is attached to this C using a double bond, plus CH3, O. But for me, if I want to write it properly so that it will not look as if I'm still a learner, I'll put this CH3 down by the side. I'll put this by the side. So this is still the same thing as saying CH3, CO, CH3 plus CH3, CO. So this is a ketone. All right, so I'm going to clean up these both and give us a reaction, and then let's twist our heads more. All right, let's look at some few examples. Now look up. There's something I'd like us to know, right? First, hot. Okay, let's finish this guy. Now, all of them, this guy will split this into two. All right, so we're going to have CH3, CH plus, supposed to be CH, CH3. But remember what I told us, we're always going to invert it so that this will actually come to this side. So when you do that, this becomes CH, CH3, CH. Now, this particular carbon here is just, this is one hydrogen attached to this carbon. So when you actually, after you must have finished breaking this bond, the next thing you're simply going to do is to introduce oxygen. Right? So we're going to convert this guy to carboxylic acid, COOH. Split this. After that, since this guy has one hydrogen, convert it to COOH, which is what we have here. The same product is what we're going to have if I had used peroxide with ozonolysis. So same thing here, COOH. Now, I decided to give us this same compound, but this time around, ozonolysis followed by zinc and acid. Recall that this same products will be formed if ozonolysis followed by peroxide is used. Okay, so I'll come here, split this guy into two. When you do that, now because of this zinc and acid, it will not allow this guy to go to carboxylic acid. This will not get to COOH. This will only stop at CH. And then you add O, that becomes an aldehyde. So this becomes CH3, CHO plus CH3 plus CHO. So that is what we have here. This converted it to COOH, one hydrogen. This one hydrogen converted it to aldehyde, CHO. Alright, so take note of that. I had earlier explained that in the previous illustration that I did. Now this time around, we are combining the carbon that has no hydrogen with the one that have one hydrogen. Alright, so when you add oxygen, when you break this guy, this part becomes CH3C plus, this other side becomes CH. But remember what I said, you have to always turn this so that this comes to this other side. So when you do that, this becomes CH. Now, this side that does not have any hydrogen will be converted to ketone. So what you simply do, you add oxygen to it. This side that have one hydrogen will be converted to carboxylic acid, because this is ozonolysis followed by peroxide, not ozonolysis followed by zinc and acid. In the case of zinc and acid, when it has one hydrogen, you convert it to CHO. If you're using ozonolysis by peroxide, it's going to give us the same products if we use hot acidic KMNO4. So this is going to give us, remove this becomes COOH. Alright? So if I write this properly, this now becomes CH3. This. So this is now what we have. Okay. So let's now look at this class. Remember, if there is no hydrogen on each of the carbon, all the three reagents, 1, 2, 3, will give us the same product. That is a ketone. So using this particular reagent is equivalent, the product I'm going to get using this, because each of the carbon of the double bond, they are not, none of them, both of them, they are not having any hydrogen. So once both of them, or once any of the carbon is not having hydrogen, it's going to give us a ketone, irrespective of any of the reagents you're going to make use of. So since this and this does not have any hydrogen, using this will give us the same product if I use this, will give us the same product if I use this. So there is no difference between these reagents when the carbon of the double bond has no hydrogen. The only difference is when the carbon of the double bond has one hydrogen. One hydrogen, hot KMNO4, and ozonolysis followed with peroxide will give us COOH. This will give us aldehyde, CHO. Alright, but when there is no hydrogen, they give us ketone, all of them. So let's start. Split this into two. This becomes CH3, CH3 plus. Please, you're going to reverse it. This is CH3, CH3. So add oxygen here and add oxygen here. So when you do that, for you to write it properly now, this becomes and this becomes okay. So this is propanone, and this is 1, 2, 2, 3 dimethyl butene, And this is 2-methyl-butene, and this is butene. Propanone, ethanoic acid, ethanol, and ethanol. Alright, so that is that for oxidation of alkanes, and I'm very certain that you must have learned something today. If you have any question, do not forget our comment section is open for that. So drop your question and I'll be right there to attend to your question. Alright, and if today is your first time watching our video class, please subscribe, share, and of course like the video. Thank you very much. Look forward to seeing you in the next class.